Hey guys, in this video we're going to learn about the concept of internal resistance and also maybe a little bit about how a voltmeter works. So I wanted to start with a very simple circuit. You can see here we have a battery and a light bulb. And so you might look at that and imagine that what we have here is a battery and a resistor. So in other words this, right? If this is a 1.5 volt battery, which it is roughly, that's all it is. It's just a battery, 1.5 volts, hooked up to one resistance. And the fact of the matter is, it isn't that. In fact, the battery itself comes with a little bit of what's called internal resistance, which actually really is not any different from regular resistance. It's just resistance that's trapped in there with the battery. So in order to talk about how we can know what the internal resistance of the battery is, we have to talk a little bit about how a voltmeter works. Now, this is actually a multimeter. If you look at the dial there, you can see there's a bunch of different settings. Right now it's in the DC volts setting. There's also an AC volts, that's for alternating current, such as what comes out of an electrical outlet in your house. And then there's other things like amps, and there's another amp section here. We'll talk about some of those other functions in later videos. For right now, the only setting we're going to use on this thing anyway is to measure volts. So if I drew a circuit diagram of what I built, this might be what I would draw, right? I've got my battery, it's hooked up to the voltmeter, and the voltmeter is always going to be indicated with that symbol right there. Effectively, though, a voltmeter really is just a huge resistance, like mega ohms. And the reason that it's got to be is because the way that you hook up a voltmeter is always in parallel with the thing that you're trying to measure. Now, this here might not necessarily look like a parallel measurement, but later on when we connect up the battery to something like a light bulb, and then we include the voltmeter in there, you're going to see, oh, it is connected up in parallel. Now, again, the reality is that what is packaged inside of that Duracell battery is the EMF source, right, which is the chemical reaction that powers it, and then also some internal resistance, which is just simply there due to the fact that the battery isn't a perfect conductor. And usually internal resistance is some smallish number, right? 10 to the negative 1 to 10 to the negative first ohms, as compared with the voltmeter, which is on the order of mega ohms. Now, if I put 1.5 volts up against mega ohms of resistance, how much current do you think I get? If you thought to yourself, I mean, like basically nothing, it would be like microamps. That would be exactly it, right? There's basically no current through the voltmeter, and that's the way you want it. If, when you hooked up a voltmeter to something, a lot of current started going through the voltmeter, then it would completely change what the circuit was. But if you hook up an enormous resistance like this in parallel with something, it barely changes the equivalent resistance at all. And thus, you can be assured of an accurate reading because it negligibly changed what you were trying to measure. Okay, so back to reality. Here we have the battery hooked up to the light bulb, and now let's add the voltmeter in. Now remember, moments ago we measured the voltage of that battery, and it said 1.47 volts on the voltmeter. It said 1.47, and that's going to be what we'll call, if you recall, the EMF, the electromotive force of the battery, which is the ideal number of volts that it provides. Reality, though, is a little different. All right, so we hooked it up in parallel to the light bulb there now. And now remember, our simple picture was, well, if we've got a battery and it's hooked up to a light bulb, and that battery provides 1.47 volts, what Kirchhoff says is all of the volts must be used. Wow, I don't know how that 4 happened. Okay, so 1.47 volts are being provided, therefore 1.47 volts must be used. But what my voltmeter says, which again is hooked up in parallel to the light bulb, is the light bulb is only getting 1.11 volts. Well, how is that possible? The battery provides 1.47. Where are the other 0.36 or so volts going? Okay, so back to this. Remember, the battery isn't just an EMF source. It's also a resistor in addition, right? And again, that's called internal resistance because there's no way to get it out. It's part of the battery itself, just like the EMF source. So both of these things here are contained inside of the battery. No way to separate one from the other. And so when we hooked up the voltmeter, like so, that's what we did, right? Voltmeter is hooked up in parallel with the light bulb, right? Does everybody agree that that's parallel because there's a junction right there? Okay, it's hooked up in parallel with the light bulb and it's measuring, 1.14 volts this time. I'm not really sure why it changed. If you wiggle the connectors even a little bit, it changes the values, but there it is. So the bulb's getting 1.14 volts. Knowing that there's internal resistance should kind of resolve this mystery for you, right? Where did the, 0.33 volts go? Well, they went to the internal resistor. The internal resistor is the thing that makes real batteries not be what are called ideal batteries. An ideal battery provides you with a fixed number of volts. A real battery provides you with, effectively, a different number of volts because the internal resistance will use some of the volts that you feel like you ought to be getting. So let's address the question now of the voltmeter and whether or not hooking that up to the circuit disturbs the circuit. So first thing is, since we hooked it up in parallel, it shouldn't do anything like, say, use up volts like it would if we hooked it up in series. But by hooking it up in parallel, right, there's a junction there, it's hooked up in parallel, shouldn't it be diverting some amount of current? And short answer is no. As we discussed, it's like 1,000,000 ohms. So if it's 1,000,000 ohms and the light bulb is on the order of 1 ohm up to even 100 ohms, it's like no big deal. The current that's going to be going through the meter is basically zero, and so it doesn't disturb the correct operation of the circuit in any meaningful way. All right, now, summarizing our results so far, this is what we've got. Battery provides 1.47 volts. The voltmeter is reading this, so that's how many volts the bulb's actually getting, and the internal resistor is therefore using 0.33 volts. All right, great. You say to yourself, so what? Why would it matter? I mean, if the internal resistance just uses 0.33 volts, I got 1.14 volts left. So if I put on more light bulbs, they'll be a little bit dimmer than the ideal picture, but, what's the big deal? Well, the problem is this, actually. The internal resistance doesn't always use the same number of volts. Remember this whole V equals IR thing. The greater the current that's coming out of the battery, the larger the number of volts that internal resistance is going to use up. So, just for fun, let's run through a couple more scenarios here. What if I draw this? I've got now the battery, the internal resistance, and it's powering 2 light bulbs. And the question is, what's the voltmeter going to read? Well, let's actually connect it up and find out. And the voltmeter says 0.88. That's horrible. That's just, words fail me. So each of those bulbs is only getting 0.88 volts now, which means the internal resistance is using up almost 0.6 volts out of the 1.7 we had left. You can see where this is going. If we hook up more and more and more bulbs, the number of volts that are going to be left over for those light bulbs is going to be less and less. Again, you might still be asking, well, so what? What does that really translate into? Well, what that translates into is the bulbs get dimmer and dimmer the more are hooked up. So we're going to take a quick look here at a simple circuit. I connected up 3 in parallel with this battery, and now I'm going to reconnect them. Oh man, when I screwed that one in, got dimmer, and even dimmer when I hooked up the third one. If you like, you can go back over those few seconds of footage there and see it again. As I remove light bulbs, the remaining one gets brighter. As I add them back in, it gets dimmer. You can see it for yourself. And that reflects what we said before about the internal resistance using up some of the volts before they even get to the light bulbs. All right, so now let's do something that you could call a quiz. So might want to get out some paper and work this out on your own. We're going to have three parts to this quote quiz, right? Part one is, as you see, okay, what if it's an ideal battery? All right, now if you missed that vocabulary term, what is the internal resistance of an ideal battery? If you thought to yourself, 0, you are correct. That's what it is. So in other words, it's literally just going to be a 1.5 volt battery hooked up to 6 ohms. All right, find the current. Good job, 0.25 amps. Of course, the reality is it's not an ideal battery. We got to deal with that now. Well, now on to part B. It says, actually, the bulb only receives 1.25 volts. If this were an ideal battery, remember the 6 ohm resistor would be getting actually 1.5 volts, and the current would be the 0.25 amps that we calculated. It's only getting 1.25 volts. So based on that information, you should be able to calculate what the current through the bulb must be if it's using, in fact, 1.25 volts. And then knowing that that's the current, you should be able to use a loop equation or some other concept to find what the resistance of that internal resistor must be. So take a moment, try and set that up, and then resume the video once you think you've got it. All right, checkpoint. The current is 0.2083. That's 3 repeating. All right, from that now, see if you can calculate the internal resistance. Also, one other hint before I reveal what it is, and that's when they give you a battery here and they say, but there's internal resistance, whether they tell you its value or not, draw in that internal resistance. So what I mean is this, since this battery is really not just that, it's in fact also that resistor, draw them. 9 out of 10 times, the reason people get confused on internal resistance problems and aren't sure what to do is because they're treating it like it's something other than what it is, which is just an extra resistor. That's all. So draw it, and then you won't forget about it and not know what to do with it. And there it is, 1.2 ohms of internal resistance. All right, if it doesn't make perfect sense, just pause, ponder for a little bit, and then we'll go on to part C. All right, so the bulb now is going to have another, whatever it is, hooked up in parallel with it, and we're supposed to figure out if the brightness of the bulb actually increases or decreases. Well, if you've been paying attention throughout this video, then you should know, based on the real-life thing that we did in that quick video, when we added more bulbs in parallel, what that does is it causes the equivalent resistance effectively to decrease, and that means the current increases. And if the current increases, that means that this internal resistor will use more volts, since V equals IR. If the total current increases, then that means that the number of volts it uses also increase. And that means that the other bulbs are going to get dimmer. All right. Now, the other question you might consider is what happens to the current through it? So effectively, when you add more things in parallel, while the total current goes up, the current to each of the individual circuit elements actually is going to end up decreasing. Okay. Whereas the total current before was 0.2083, as an exercise, you can work it out, and you'll come up with, it goes up to 0.47, but the current through the 6 ohm resistor will decrease from that 0.2083 number down to about 0.16 or so, I think. Okay, you can work it out yourself if you want, just as an exercise again. But if you can get that number, that 0.16, then you will have another way of demonstrating, oh, look, it's going to get dimmer because the current going through it decreased. Okay, I think that's just enough about internal resistance. I hope that was informative and helpful.